Okay, so we're going to prove that if A is any event and C sub 1, C sub 2, all the way to C sub n form a partition of S, then we know the probability of A is equal to the sum of all these probabilities here, right? So this theorem is just the general version of the two previous theorems. So we're going to use those two previous theorems in order to prove this theorem. Okay, so proof. Of course, we can't use a picture because there's n of these, right? I mean, I guess we could, but we don't need to. All right, so proof, we're going to start with C sub 1, C sub 2, C sub n form a partition of S. So, of course, this implies that S is equal to the union of these sets, right? C sub 1, union C sub 2, union dot dot dot, union C sub n. And all of these pairs within this family of sets, right, their intersections are empty. So the way we can write that, so let me go ahead and scoot down a little bit. The way we can write that, and C sub I intersection C sub, that's a J. C sub I intersection C sub J equals the empty set, right, for all I not equal to J. So what this is saying is that I know that any two of these sets that I put together with an intersection, that intersection of those two sets would be empty. So for instance, if I were 2, J could be anything but 2, so J could be like 7, right? We know C sub 2 intersection C sub 7 would be empty. So that's how this statement is being used. Okay, so now we know, so let me go ahead and draw a picture to sort of illustrate my point that I'm going to make next. So we have S and we have A, right? So what I'm going to say in my next part of my proof is that A is equal to A intersection S. I think that is pretty intuitive based off the picture, right? Because, as you can see, A is the shaded area, and A intersection S is all the elements in A that are also in S, right? So that would be also the shaded area. So A is equal to A intersection S. And previously, we showed that S was equal to C, the union of these sets, right? So this is equal to A intersection C sub 1, union C sub 2, union dot dot dot, C sub n. And now using the distributive law, or distributive property of sets, right? This is equal to A intersection C sub 1, union A intersection C sub 2, all the way to A intersection, or union, union, A intersection C sub n, right? Where all of these are mutually exclusive, right? Since all the C's are mutually exclusive, then A intersection the C's would also be mutually exclusive. So where this family, right? So let's call A intersection C sub k, where k goes from 1 to n, right? We know this family is a family of mutually exclusive events, right? And then, of course, we're going to use axiom 3 again, right? So this implies, so since A is equal to the union of these sets, right? This means that the probability of A is equal to the union of those sets, or the probability of the union of those sets. So A intersection C sub 1, union A intersection C sub 2, union dot dot dot, union A intersection C sub n, right? And then, of course, since these are mutually exclusive events, this is equal to, by axiom 3, the probability of A intersection C sub 1 plus the probability of A intersection C sub 2 plus dot 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 plus the probability of A intersection C sub n. And that is exactly what we wanted to show.